everyone, and welcome to the 7th session of the ISRM Young Members Seminar Series. My name is Ryota Hashimoto from Hiroshima University, Japan, and Dr. Zihong Zhao from Tsinghua University, China.
Everyone, and welcome to the 7th session.
And I, as part of the ISRM Young Members group, are happy to chair this 7th monthly seminar. It is a great pleasure for us to be here today, and we would like to thank you for attending this session. Before starting, we would like to thank the support from the International Society for Rock Mechanics and Rock Engineering, and especially to Sevda Dekoda, ISRM Vice President for Australasia and Chair of the ISRM Young Members Committee. We also would like to thank all the young member representatives of national groups that have joined this initiative. Finally, we would like to thank Dr. Chun Zhu and Dr. Lan Liu for agreeing to present their work in this session. Before our speakers begin, we will take a moment to present key information about the seminar series. This project attempts to promote youth community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and the academia, and to strengthen relationship between different countries. We would like to invite a variety of young members to participate in this seminar series. The criteria for speakers are shown in this slide. So being an ISRM member and having a maximum age of 35 years or of 40 years if a PhD degree was obtained in the previous 5 years. And having worked in rock mechanics and rock engineering for a period no longer than 10 years. Speaker nominations can be made by the nominees national group or by some other person or organization acquainted with the nominee's work. Self-nomination are also accepted. Nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. On the screen, you can see our contact email address. This webinar will be held every month, and we invite you all to keep in touch. Okay, so now we will begin the first seminar of the first presentation of today's session. So each presentation will last 20 minutes and will be followed by 10 minutes of Q&A session. For the smooth running of the seminar, please turn off your camera and microphone during the presentation. And if you have any questions, you can use chat and also the raise hand feature from the reaction. So, okay, let's move on to the first presentation. The first speaker is Dr. Chun Zhu, who is currently working as a professor at the School of Earth Sciences and Engineering, Hohai University, China. Dr. Chun Zhu holds a Master of Science degree in Civil Engineering from China University of Mining and Technology in Beijing, and a PhD degree in Geological Engineering from Jilin University, China. His research focuses mostly on the deep rock mechanics and engineering disaster monitoring. Today, he will be presenting a talk entitled innovation of giant NPR cable and its advantages in critical slip warning for landslide disaster. So, Dr. Zhu, please start the presentation.
Thanks for your introduction. I will share my screen. Good day, everyone. I'm very honored to participate in this academic report of ISRM Young Members Seminar. I mainly report this research from 4 parts. First of all, I will report the research background. With the rapid development of engineering construction, such as the famous Three Gorges project, the Qinghai Tibet Railway, and so on, engineering disturbance-induced landslides have become the main types of geological disaster in our country. Statistics in the past 10 years show that landslide disaster remain high, and among them, landslide disaster accounted for more than 55% in the past 3 years. In essence, landslide is a sensitive response of block movement, and it has a damage feature from small deformation to large deformation. We can see that in the field of mining engineering, transportation engineering, national defense engineering, and industry and civil construction engineering, the large deformation of landslide pose a serious threat to the safety and the stability of these major projects. In order to control landslide disaster, reinforcement methods such as lattice beam, anti-slide piles, and pre-stressed anchor cables were adopted in these projects, but many unfortunate landslides still occurred. For example, in April 2010, the most serious landslide disaster in the history of the highway engineering occurred in Keelung rainfall section of Taiwan, number 3 highway. In July 2020, the slope reinforced by anchor net spring in Xiongjashan Quarry in Yunnan province occurred a landslide disaster due to the rainfall, and the rainfall slope was seriously damaged by tension cracking. According to the research, whether the natural landslide or the engineering-induced landslide, their essence is the same, and they all experience a mechanical process in which geological bodies deform first and then undergoes movement damage. We all know that the deformed body before the landslide can be described by Hooke's law, and the moving body can be described by Newton's second law. But how to describe the transformation from deformed body to the moving body? This is a major scientific problem. Professor He believes this may be the way to overcome the difficulty of critical sliding warning. In order to solve the above scientific and technical problems, we have carried out a lot of research, and the following 4 innovation points have been obtained. Innovation 1, material innovation. A new material of giant NPR, negative Poisson ratio cable, is developed. Through the combination of conventional material and the NPR constant resistance device, the NPR effects of PR material is realized. The PR material used in the traditional slope reinforcement is generally damaged by the large deformation, such as the cable breaking, lattice beam shearing, and so on. which eventually lead to the overall instability of the slope. The reason for the above phenomenon is that currently used reinforced material is a small deformation material, which cannot bear the large deformation and is partially naked and broken under tension, which is a kind of Poisson effect material. The solution is to develop a new material with constant resistance and large deformation, which has the mechanical properties of thickening when stretched. Based on the concept of NPR structure proposed by Professor He in 2006, a new type of NPR structure was designed and developed, which can produce volume expansion when under tension. On this basis, the relevant mechanical models and constitutive relations are established. The constant resistance design formula was deduced, and it is found that the constant resistance value of the NPR cable only depends on the elastic parameter of the constant resistance casing and the geometrical parameter of the constant resistance body, and does not depend on the external loading. The large deformation numerical calculation model and the mechanical analysis method of the NPR were constructed. The mechanical behaviors under the static tension are explored in depth. In order to meet the needs of different landslide projects, a series of NPR cable products with different consistent resistance specifications have been developed, which are respectively suitable for the engineering needs of small landslide, medium landslide, and large landslides. The innovation 2, system innovation. The testing system and the experiment method for the mechanical properties of giant NPR cable were developed, through which the supernormal mechanical properties of giant NPR cable material with high constant resistance and large deformation have been verified. In order to test the supernormal mechanical properties of giant NPR cable, a series of mechanical test systems were invented, such as the 100-ton and 200-ton static tension test system, and the job hammer impact test system, and the Hobson impact tension test system. After testing, the new material of giant NPR cable has 4 remarkable supernormal mechanical properties. The first supernormal property is NPR effect. Experiments have shown that the expansion of the giant NPR cable before and after tension can reach 3 to 4 millimeters, which has an obvious negative Poisson ratio effect. The second supernormal mechanical property is high constant resistance and large deformation. After testing, the product all have the mechanical properties of high constant resistance and meter-level large deformation. The constant resistance value is about 850 kilonewton, and the maximum deformation can reach to 2000 millimeters. The third supernormal mechanical property is energy absorption through the infrared camera and laser temperature measurement equipment. The heating effect of the giant NPR cable during the static tension process was obtained, and its energy absorption mechanism was revealed. The fourth subnormal mechanical property. Under the impact load, the giant NPR cable can bear multiple impacts without breaking. The innovation 3. Theoretical innovation. A physical simulation experiment system for landslide Newton force have been developed, and the scientific phenomenon of sudden drop in Newton force indicates a landslide will occur have been found. Finally, the Newton force change law of geological disaster have been established. Before scientifically predicting landslides, we should further find the necessary and sufficient conditions for the occurrence of landslides. Since 1994, Professor He has led our group to research this issue, and a method for measuring the Newton force on the potential slide surface was proposed. Then, the double block catastrophe mechanics model was established. The indoor physical simulation experiment system for monitoring Newton force is developed. Through massive experiments, the scientific phenomenon of sudden drop in Newton force indicates a landslide will occur is discovered, and it is verified in landslide similarity ratio physical model experiment. Newton's force change law was established, which classifies the rock mechanics interpretation during the transition from Hooke's deformation law to Newton's motion law, and revealed the core problem that the catastrophic time is proportional to the mass of the geological body, and the catastrophe displaces, and inversely proportional to the Newton force. Innovation 4. Technological innovation. The integrated technology of landslide whole process monitoring and critical sliding early warning based on giant NPR cable have been developed, and the problem of integration of landslide large deformation disaster reinforcement monitoring and early warning have been solved. Based on the above basis and the new NPR material, a Newton force monitoring and early warning hardware system for landslide disaster have been developed, including giant NPR cable force measurement system, intelligent sensor acquisition system, integrated protection system, solar power supply system, and big data transmission system. The matched software platform for big data processing and early warning information release have been developed, and the software copyright have been obtained. The Newton force monitoring and early warning criteria and the model for landslide disaster have been established through the analysis of a large number of numerical simulation physical model experiment and field measured curves for early warning modes of stability, potential instability, cracks, and slips are proposed according to the changing features of Newton force with time. And based on the above four modes, the corresponding for computer intelligent recognition criteria of blue early warning, yellow early warning, orange early warning, and red early warning are developed respectively. By using the above equipment system, the phenomenon of sudden drop in Newton force indicates a landslide will occur was monitored on site for 16 times, which is the scientific of Newton force change law was verified. These figures are the Newton force monitoring and the critical sliding warning curve of the metamorphic landslide. These figures are the sedimentary rock landslide. These figures are Lewis landslide. Through the analysis of the above case, a total of 16 landslide disasters occurred in the past 10 years, and this system all issued a critical sliding warning 3.5 to 20 hours in advance, effectively improving the precision and accuracy of critical sliding prediction for landslide disaster. Compared with the other similar technologies in the world, it is found that the giant NPR cable material is superior to the existing large deformation material in various indicators, such as constant resistance value, deformation value, and energy absorption. In terms of landslide disaster monitoring technology, the Newton force monitoring parameter, which is a sufficient and necessary condition for landslide, can be used. In addition to the function of monitoring and early warning, and can also reinforce and protect the slope. And it can issue a critical sliding warning 3.5 to 20 hours in advance. At present, this technology has established 600 Newton force monitoring points in 23 provinces in China, involving 8 engineering application fields. The following is a detailed description of the critical sliding warning process based on the 3 recent application cases. The first one, taking the Nanfeng open pit iron mine as an example for analysis. Since the Nanfeng open pit iron mine has applied this technology up to now, the phenomenon of sudden drop in Newton force indicates a landslide will occur was monitored in Nanfeng open pit iron mine for 10 times. This is the plant distribution feature of the landslide area on January 4, 2019. This is the monitoring point location and the cross-sectional view of 2019 landslide of Nanfeng open pit iron mine. This is the on-site aerial photo of the 2019 landslide. Due to the disturbance caused by the slope expansion and excavation, the original landslide accumulation continues to expand to the pit bottom, resulting in a new landslide. This is the monitoring curve of the whole landslide process. It can be seen that the monitoring curve suddenly rose on August 14, 2018. The cracks continued to develop and penetrate, and the system issued long-term warning information. At 1959, on January 3rd, 2019, the monitoring curve suddenly job. And the system issued a critical sliding warning information according to the early warning guidelines. And at 9:12 on January 4th, 2019, the landslide disintegrated and slipped, and the landslide occurred. The trailing edge of the landslide sank 7 to 8 meters, and the pre-slip warning time was advanced by 13 hours. This is an enlarged view of the 2019 landslide Newton force monitoring and warning crew at the critical sliding stage. It can be clearly seen that when the Newton force suddenly dropped and the landslide occurred. Application case 2. Take the landslide of Xiongjia Quarry in Tongchong, Yunnan province as an example. Xiongjia Quarry is the only stone supply for the construction of Cangdifang Reservoir. With the influence of mining disturbance, cracks gradually develop on the slope, threatening the safety of quarrying machinery and worker. 4 Newton force monitoring points are installed in the quarry. This figure shows the slope monitoring section, and the giant NPR cable is buried at a depth of 35 meters. This figure shows the on-site reinforcement and monitoring conditions of the slope, and the 2020 landslide is located at this position. Our system issued a mid-term warning information at 19:06 on July 1st, 2020, and issued a short-term warning information at 21:3 on July 4, 2020. Subsequently, at 1:39 on July 5th, 2020, the further critical sliding warning information were issued. But the landslide did not occur, and the second critical sliding warning information were issued at 13:55 on July 6, 2020, and the third critical sliding warning information were issued at 12:26 on July 9th, 2020, and the landslide disintegrated and slipped at 29 on July 9th, 2020. The early warning time is 7.5 hours. This shows the failure feature of the whole landslide process. The slope further cracks and then expand rapidly, and eventually disintegrate and slip. This is the failure feature of the slope. Platform cracked and sank, and the scattered body slump occurred on the left foot of the slope. This is the failure feature of structure reinforced by the PR cable, and the failure phenomena such as cable breaking, anchor pier compression, and lattice beam breaking were occurred in the field. Application, the third case, take the landslide of Liangyong Highway in Sichuan province as an example. We have placed 5 Newton force monitoring points along the Liangyong Highway in Baoxing City. This is the layout section of the Newton force monitoring point. This landslide occurred near Baoxing number 3 and Baoxing number 4 monitoring points. This figure shows the Newton force monitoring crew. According to the early warning criteria and mode, The system issued the medium and the long-term early warning information at 1848 on August 23, 2020, and the Newton force increased by 70 kilonewton. At 10:50 on August 27, the monitoring crew suddenly dropped, and the system ensured the critical sliding warning information. After 3.5 hours, the landslide occurred, resulting in the settlement and the collapse of the highway around the landslide area, with a maximum settlement of about 40 centimeters. This is the feature of cracking and slip failure of slope and those near portion number 3 monitoring point. This is the change factor of Newton force crew of portion number 4 monitoring point, and the system issued a critical sliding warning information 5 hours in advance. This is the feature of cracking and slip failure of slope near portion number 4 monitoring point. This is the end of the analysis of the application cases. The above is my presentation. Thanks for your listening.
Thank you very much, Dr. Zhu. And now we would like to start a Q&A session. If you have any question or comment, please raise your hand, or there's a question on the chat from Mr. Taoli. Can you see, Dr. Zhu? Can you see the chat?
The question is showing the talk box. How to model this NPR board in AppQuick? Is this question? Oh.
Yes, that's the question.
Oh, yeah.
Hi, please.
This question is interesting, and we use a new model to construct this NPR board because the NPR board is different from the existing board. That we can make establish a new model. If you interested in the new model, we can talk later. You can send the email to me, and I will show you the specific model.
Oh, there is another question on the chat.
Dr. Zhu, you can read the question because some audience in the YouTube, they cannot see the question.
Okay, sorry.
Okay. We all know when the landslide occurred, I think the force first change. I think the force is more directly compared with the displacement. The force is difficult to measure, but we can use the pre-stress force. and we can measure the point stress force to calculate the complex force system. But how to keep sorry. We can talk it later. I think these people is Chinese. We can talk later after this meeting by Chinese.
Okay.
Maybe more directly and.
Okay. Okay. Is there any question from the floor? Can I ask a question? Yeah. I was in. Can you hear me?
Oh, yes, we can hear you.
Okay. Thank you.
Stop.
Yeah. Okay. I was impressed with the fact that the result that your system has already measured several actual real landslide events. So because when we develop a measuring device, it's the most difficult point is how to select the measuring point to get the to get a result of the actual landslide event. So can you explain how did you select the measuring point in the site?
Dr. Zhu, can you understand the question?
Okay. I cannot listen that question clearly.
Okay. If you cannot hear well, you can answer to the questions on the chat.
Dr. Zhu, you have 2 more questions in the chat box. Can you answer that?
Okay. Firstly, we can drill the hole to determine the potential sliding surface, and we can throw the geological survey, and also use some numerical simulation software to comprehensive the potential sliding surface. And I think the critical slip is mean when the landslide occurred shortly, and it can give us the sufficient time to sell the equipment or worker. That's all.
Okay. Any other question or comment? No more question? If there is no more question, we would like to move on to the next speaker. Thank you, Dr. Chu, for the great presentation.
Thank you. Thank you. Dr. Ryota, could you please share the screen?
Yeah, sure.
Yeah. I will chair the second speaker, Dr. Liu Lang, yes. Okay. Let me introduce the next speaker of this webinar session. And the next presenter is Dr. Lang Liu, who has recently obtained his PhD in geotechnical engineering at the University of Alberta, under the supervision of Dr. Rick Cholentnik and Dr. Derek Martin. He obtained his master's degree in geotechnical engineering at the University of Alberta and a bachelor degree in safety engineering at the China University of Mining and Technology. His research work varies from underground coal mining hazard prevention to petroleum and mining geomechanics. His research work at Alberta focuses on application of pressure meter testing in shales and the development of interpretation methodology for in-situ stress and geomechanical properties. He is also experienced in lab characterization and constitutive analysis of weak rocks. Today, he will be presenting a talk titled Reconciliation between laboratory and in-situ measurements of elastic stiffness for Opalinus clay. So, Dr. Liu, please.
Okay, thank you, Dr. Zihong. I will share my screen now. So can everyone see my screen?
Not yet? Yes, you can start. It's okay.
All right, thank you.
Thank you.
Good morning and good evening and good afternoon, depending where you are. It is my pleasure to be here in this ISRM Young Members Seminar to present a major part of my research work on the topic of reconciliation between laboratory and in-situ measurements of elastic stiffness for Opalinus clay. First of all, I'd like to give my thanks to ISRM for this opportunity. I also like to acknowledge my research group, the Reservoir Geomechanics research group in Alberta, University of Alberta. I also like to acknowledge NIGRA, the Swiss National Cooperative for Radioactive Waste Disposal, and that initiated this study and also provided lots of support during my PhD study. In the following presentation, I'd like to cover these 5 parts. First, I'll start with research background and motivations. Then I move to our recent test campaign at the Monterey Rock Laboratory in Switzerland. Then I will show how the laboratory and in-situ test results can be reconciled. Then I move to my modeling study of the elastic stiffness evolution for traction and pressure loading path. In the end, I will summarize and conclude. So the deep geological repository is an underground research, it's underground facility to isolate some radioactive waste for thousands of years. And here it shows the typical layout of the high-level waste repository. The Opalinus clay is chosen as one of the designated host formations for the repository construction in Switzerland because of its low permeability and also its potential of self-healing. So there will be multiple stages of loading and unloading during the development of a repository. At each stage, the deformation of the ground should be carefully evaluated. Therefore, it is very important to characterize deformation properties for both intact host formation as well as disturbed rock mass, for example, in the EDZ excavation damage zone. In this study, I will mainly focus on the elastic deformation property. Of course, we know there are challenges in the characterization of elastic stiffness for this type of wake rock, including its stress and strain dependencies, its sensitivity to disturbance, its anisotropy, and also its heterogeneity. So the determination of the rock mechanics properties mainly relies on the laboratory testing on the specimen at a centimeter scale. The specimen at this size may not represent the Opalinus clay at a larger scale, where the strong heterogeneity and also the fractures can be present. Also, the lab specimen extracted from the rock cores can be heavily disturbed due to coring and the specimen preparation process. And this disturbance is particularly evident in wake shields. Although there are some recent improvements to minimize this disturbance, however, it is still necessary to assess the lab properties with testing results from the other testing methods, for example, from in-situ testing. However, we know that these are two different types of tests, and they are conducted under different loading conditions. And like lab test, the rock for in-situ testing may also suffer from a certain degree of disturbance by drilling. So these are the challenges I had to face to compare the laboratory and in-situ properties for Opalinus clay. So how is the elastic modulus determined? I'm sure this is not a new topic to everyone. And to the left, it is a cover of the book of the ISRM suggested methods, which shows the possible ways to determine the Young's modulus for conventional uniaxial composition test. And for testing on wake rocks, the nonlinear deformation makes it difficult to justify which portion of stress and strain curve to use for the modulus determination. In fact, the monotonical loading on the rock specimen induces an elastic deformation due to microfracture closure and sliding. And the modulus obtained from this unloading slope does not represent the true elastic behavior. Instead, it was demonstrated both from theories and from experiments that unloading from a current stress level can sufficiently inhibit the frictional behavior, and the modulus determined using this unloading step and can better represent the elastic properties of the wake rock. So for this reason, only the unloading modulus is considered in this work. For in-situ rock modulus measurement, there are established methods, including pressure testing, and pressure is usually called a dilatometer in the rock mechanics community. For parabolic pressure testing, the probe is deployed in a borehole, and then the compressed air or the fluid is injected into the pressure probe that allows the borehole to expand under a controlled pressure increase. And for Cambridge type pressure meter, the radial deformation of the borehole is monitored by a set of caliper sitting in the middle plane of the probe. And the radial deformation captured by different caliper arms can be different at different axes. And typically, the averaged response is used for the interpretation based on the Cambridge expansion theory. Again, for testing in wake rocks, the modulus obtained from this unloading step is considered more representative of the elastic properties. And this study is mainly established on a recent field campaign at Montreal Rock Laboratory in Switzerland. And in this underground research laboratory, we have 3 test boreholes, borehole BGC2 and borehole BGC-A4. Both were drilled perpendicular to bedding, and the borehole BGC-A6 was drilled parallel to bedding. And all the test boreholes were drilled using air flush, and there are geological and geophysical logging after drilling. And the pressure meter tests were conducted at different locations of each borehole. And we also select some rock cores preserved for the rock mechanics testing later in the lab. So let's look at the lab test first. And from the rock cores, and the specimens were cut with different orientations for structural tests to evaluate the impact of rock anisotropy. In each test, the rock specimen initially loaded to a certain effective confining stress before structural loading. And during structural loading, the unload-reload cycles were performed respectively at the early pre-peak stage and also at the post-peak stage. And the Young's modulus was determined using the linear regression on the unload data, and the nonlinear deformation is also observed during this unloading step, where a variation of the second modulus can be derived over this small unloading string. And this slide shows the summary from the lab tests. It shows that at the post-peak stage, the elastic modulus of the rock is reduced because of a shear-induced damage. And the second plot shows the impact of rock anisotropy. The modulus obtained for the spaceman loaded parallel to bedding is about 2 or 3 times higher than that for the spaceman loaded normal to bedding. Let's also look at the pressure test. And for the pressure test in the stiff ground, one important step is to calibrate system compliance. And this is done by conducting an inflation test in a steel thick wall cylinder. And the deformation of the system at different pressure levels can be calibrated and then used to correct the field test data. Ideally, in the pressure test, the material point near the borehole is subjected to the plane strain shearing with the changes of the shear strength and shear strain at the same time. Therefore, we can use the relationship. Between the expansion pressure and cavity strain to determine the shear modulus of the rock. And in our test, we performed multiple small unloading steps at different pressure levels, and the shear modulus can be evaluated either using the linear fate on the unloaded data or the power law fate to describe the nonlinear elastic deformation over the unloading shear strain. And this second approach allows me to determine the variation of the second shear modulus with unloading strain increment. And this summary plot shows the shear modulus determined using all the unloading steps in different tests from these 2 boreholes. And it shows the increase of the modulus with the expansion pressure for the first 5 MPa. And the modulus becomes more or less constant after the 5 MPa. And the comparison between the results from these 2 boreholes also shows the effect on the strong effect of the rock anisotropy on the determined shear modulus values. We can also observe the variation of the shear modulus with borehole depths in each borehole, which shows the degradation effect of the rock mass disturbance in the excavation damage zone, and also the effects of the local fracture in a testing interval that can also reduce modulus value. So the big question is, how are the structural test results compared with the pressure test results? Now we'll only consider the cases with loading parallel to bedding for both tests. For laboratory test, we can calculate the shear modulus using the measured Young's modulus and Poisson's ratio for the same orientation, and then compare the shear modulus obtained from the pressure tests. And this figure shows the decay of the second shear modulus with a small strain increment in unloading step from both tests. And an invariant shear strain measure, delta gamma S, is used here to count for the difference in boundary conditions in these 2 types of tests. And this comparison shows the modulus obtained from the unloading step at a higher pressure in pressure tests approaches to that obtained from the first unload at the pre-peak stage of the structural test. And these curves maybe represent the intact properties of Opalinus clay, while the modulus obtained at a lower pressure of pressure test is close to the degraded modulus obtained at the post-peak stage of the structural test. Finally, we can evaluate the modulus at a constant strain increment, for example, at 0.1% for the green curves obtained from the other tests. And the modulus evaluated at this strain increment has shown a good agreement between these 2 types of tests. Although the lab tests also shows a certain degree of dependence on the effective confining pressure. And the effect of the rock anisotropy is further investigated using the measurement of the borehole deformation at different caliper axes. And from each axis, the directional modulus G star is calculated, again, using the unloading step. And the G star is generally isotropic for the pressure loading parallel to bedding, but it shows a certain degree of anisotropy for the pressure loading partially normal to bedding. To explain this anisotropy, I considered the Opalinus clay as a transversely isotropic elastic material and calibrated those isotropic elastic parameters using both structural S test and structural P tests on the intact specimens. And these parameters values were then used in an analytical solution derived by Amadei and Savage for cavity expansion in the borehole with this particular orientation in a transversely isotropic elastic medium. And the prediction shows a reasonable agreement in orientation with the field data, but slightly overestimates the magnitude. And this overestimation will be explained in the next slide. Now, from the borehole camera image taken before pressure test, and we identify the frequent borehole breakouts located in the direction normal to the bedding plane. And this type of damage caused by structural instability after an unloading from the borehole is consistent with the other observations using the overall core of the borehole that was drilled with the same orientation. To understand how this would affect the pressure test, I built a simplified finite element model for a quarter borehole, and the background median is defined using the laboratory calibrated transversely isotropic elastic parameters. And in addition, an elliptical stiffness degradation zone is imposed to mimic local borehole damage. And the modulus G star can then be estimated using the predicted borehole deformation at different azimuths theta. And it shows a better agreement with the pressure measurement when this local borehole damage is considered. Another thing that we are particularly interested in is the change of modulus with stress in both structural test and pressure test. Here it shows the evolution of the modulus measured along different loading path, and the multiple stage structural test data reported by Grasso and Plishik are used here. It has the multiple unloading steps, and the variation of the unloading elastic modulus for both pre-peak stage and the post-peak stages can be determined. And for this test, I explicitly modeled the stress dependency of the elastic stiffness tensor for Opalinus clay, assuming its variation as a function of the three principal stresses. And the expression for Young's modulus is reduced to be as a function of the actual stress for structural loading. And the scalar damage variable is also introduced here to account for the modulus degradation at the post-peak stage. To complete this constitutive model, the damage function based on the tensile strain tensor and the yielding function based on the stress are also formulated. And all of these formulations can be integrated into this workflow to solve for the stress change given a strain increment. And the details of this workflow can be referred to another paper we recently published. And the total of 8 model parameters are then calibrated, and the prediction for the multi-stage structural test shows a good agreement with the test data. And this constitutive model is further implemented into a finite element code uppercurse to predict borehole deformation during borehole unloading and unloading. And for a simple demonstration, an asymmetric borehole model is considered to predict for the case with an isotropic in-situ stress. And the use of a stress-dependent stiffness functions predicts nonlinear elastic deformation. And since the current model cannot reproduce the hysteresis of unload cycles, I use the tangent line on the predicted curve to estimate the pressure shear modulus. And this prediction is further extended to the case where the extensile microfractures can be induced by drilling unloading. At the first stage of the modeling, after the release of the pressure PC, a near borehole damage zone with a degraded modulus is predicted. At the second stage, the pressure is reapplied to the borehole wall to mimic pressure loading, and the recovery of the elastic modulus is predicted. The change of pressure shear modulus was then estimated from the expansion curve. And when the pressure is recovered to an in-situ stress level, it shows a lower magnitude than the case without borehole damage. And in a parametric study, I also showed a case with a higher maximum damage limit, and it predicts a larger extent of borehole damage zone and causes more reduction of pressure shear modulus. So this concludes my presentation, and I'd like to summarize. In this study, the elastic stiffness was determined using unloading steps from high-quality laboratory and in-situ measurements. And despite at different scales, the agreement between these two types of tests was established for the Opalinus clay when all these factors are considered. And an elasto plastic damage model incorporating the stress-dependent elastic stiffness were proposed and then implemented in a finite element code. It effectively quantified the modulus evolution from both structural tests and in-situ pressure tests. And the modulus measured from pre-board pressure tests can be reduced by the initial borehole damage after drilling unloading, and it shows it cannot be recovered even when the borehole is reloaded back to the in-situ stress level. So I think the last one is the most important one. This study has provided a valuable example and guidelines of characterizing the elastic stiffness of weak shields. it gives us tremendous confidence using our current procedure to characterize and to model the modulus for this type of rock. I'd like to just highlight the references I used in this presentation. Of course, I need to just acknowledge those people because this research cannot be done without support from them. First of all, my supervisors, Dr. Martin and Rick Chartonic, and also Dr. Silva Giger and Wena Grasso for their valuable laboratory test data, and as well as this valuable on-site assistance for preprint testing from my colleagues at the University of Alberta and other colleagues from Swiss Topo and Switchshell. Of course, I would like to acknowledge the contribution from these two perimeter testing companies, and I'd also like to acknowledge the financial support by the energy simulation industry research consortium in the Georgia mechanics. So that's the end of my presentation. Thank you for your attention. I'm happy for any questions you have.
Thank you very much for your excellent talk. Thank you, Dr. Liu. I think we have 10 minutes for the question and answer session. Does anyone have any questions? Okay, already I think we have a couple of questions in the chat box. The first one is about thank you for your presentation, how to measure size of BDZ. Could you please give more criterions to classify BDZ? I don't know BDZ in your talk.
It stands for Bohol damage zone. That's a good question. So in this talk, I didn't show our measurements for the size of BDZ, but in fact, there are some ways to measure that. For example, you can use in this study we have the we call it interval velocity measurement, which uses a multi-channeled ultrasonic probe. I think I have some figures to show, maybe just give you better ideas of what it is. I can share my screen.
You have figures in your slide? Yeah, we still can see your slide. If you have figures in
now you can see my screen, right? Can you see my screen now?
Yes.
Yeah. So we have this we call it a multi-channeled ultrasonic probe. So it's sending the wave from the emitter, and the wave can be received by different receivers behind this emitter. Then you can determine the wave velocities for each ray. And this gives you the data that you can use for the tomographic inversion analysis to determine the radial and also longitudinal variation of the velocity. This can certainly give you some sense of how the velocity or modulus changes from the Bohol wall to the far field. This can give you some estimates of the Bohol damage zone. That's just one way to do that. However, there's some limitation with this method too, because we know the Opalinus scale is strongly affected by the moisture and saturation. So what you made here might not directly represent the degradation of the modulus, possibly just represent the variation of the saturation. So we need to do a careful evaluation to decouple those two effects in order to identify the real BDZ. Hopefully I answered this question. Yeah.
Thank you. I think we have two more questions in the chat box.
Yes.
The second one is about thank you for your presentation. After post-peak, the rock is no longer elastic materials. How can you measure its elastic modulus?
Yeah, that's also a good question. That yeah, you're totally right. When at the post-peak stage, the rock is sheared, and now the deformation is is a result of the sliding of a shear plane. However, after you do unloading, I think the sliding of this shear plane would be stopped. Now things just like the whole rock specimen will be reloaded, just rebounded elastically. In that small reloading strain, that probably represents more dominant by the elastic deformation rather than the frictional behavior of the rock. But I totally agree that the rock is no longer elastic material after the shear failure. So what I actually measured during this unloading at the post-peak stage is the response of both the solid rock and also the shear fractures.
Okay, the next question is from Taolin, and thank you very much for your interesting talk. I noticed the modulus in unloading process is considered. Besides elastic deformation, there may be also be some damaged particles during unloading. Whether these processes can be analyzed in your model.
Yeah, so if I understand right, the question is that when you're unloading, you can also damage the sample. But I think the extent that you can damage sample in unloading should be already after a large deformation. So in my test, I think the unloading is only for a very small strain. It doesn't really necessarily further damage the sample. And even unloading, we can see this, even at this small unloading string, we can see the linear elastic deformation behavior of the rock. So that possibly means there's kind of like frictional behavior, even in this small unloading step. I didn't really consider that mechanism in my modeling. I think it's really hard to model at this stage, but I'm probably going to incorporate in the future to model this linear elastic deformation during unloading.
Yes, thank you. Do we have more questions from the audience? Yes, I would like to ask two more general questions. One is about the scale effects. I think your work is quite interesting. You have LAM test and also in-situ data. And for rock mechanics, we always know the scale effects is quite difficult one to consider in the model. Yes, you have this data, and I don't know in your model, do you have some idea to consider scale effects? And the other question is, for nuclear waste repertory, we know that in addition to the in-situ stress, maybe also suffered from high temperature, and like you said, moisture or something. I think it's coupled processes is also an important issue. So what's your opinion to extend your model in the future to consider these coupled processes? Thank you very much.
Yeah, thank you a lot, Dr. Zhu, for these great questions. So first one, scale effect. In this investigation, we compare the specimen at the centimeter scale with the pacemaker testing at about meter scale. Definitely for the interval of pacemaker testing at that scale, we have a heterogeneity of the little faces because Opalinus is very heterogeneous. And so for example, when we're doing a test in the sanding faces of Opalinus clay, has a strong variation of the methodology, even in this 1 meter. So definitely there's a scale effect, because in laboratory testing, you're always testing a small specimen, only represents a certain little faces. Yeah, but in this study, we didn't really see the scale effect. Like I just presented, we're comparing the two type of tests, and in the same borehole, and we can see the agreements between the lab test and the pacemaker test are pretty good. So which means for the centimeter scale to the meter scale, there might not be a strong effect of the scale. Maybe if you go smaller to the millimeter scale or micron scale, that will show a strong effect of a scale, because now you're investigating the green and compared to the big specimen. Yeah, I think that's something we should also look into more, because that's not that's one more objective of my study, but we didn't really see the scale effect in this comparison. The second question is the coupling effect. I think that's also great questions. You know, like even in this study, in structure test, where you only use the undrained structure test, and the impression testing, we're actually not quite sure what is the drainage condition. We don't actually understand how the pore pressure changes at different locations in the rock during pressure testing, because there's no way to measure it. So even we can consider the coupling effect into my modeling, but there's no sense for me to verify. But I think that's a good, that's an important mechanism to incorporate into the modeling framework. However, we need more data just to make sure that coupling effect is important in this modeling work. We need more independent measurements, either in the lab or in situ, just to make sure all the mechanisms considered in the modeling is necessary. Otherwise, we'll just create lots of modeling, just introduce lots of parameters in your model, but there's no way to calibrate or verify them.
Yeah. Yeah, I think
hope that not.
Yeah, time is almost up, but we have one more question. I think it's the last question for you. Yes, thank you very much for your interesting talk. I have a general question about the host rock of nuclear waste repertory. Many countries choose granite as the host rock of nuclear waste repertories. Could you please compare granite and clay as the host rocks of nuclear waste repertory? Yes, I think it's interesting. Yeah, you focus on clay. I don't know if you think about or consider granite. What's difference between these two kind of host rocks? Yeah. I hope you can give a very simple answer. Thank you.
Yeah, that's a question that is too big for me to answer. So I didn't have much experience with granitic rocks for the nuclear waste disposal. I think you're right. That's one of the another options for people choose to be as a repository. I think it's for the granitic rock, there are probably also some difficulties. Like you still have to be very clear about the geologic condition of the host formation. You understand how the fracture distributes and how the nuclear waste would what if the leakage, how the rock responds. For the sedimentary rock like clay shales, I think one of advantages maybe it's low permeability, and also there's a vast abundance of clay shales everywhere almost, and it's not very deep. So that's why you can easily have access to those repository because it's shallow. And another important characteristics of the, for example, Opalinus clay is its self-healing properties. So after its intake of some moisture, so if there's a fracture before, then the fracture would be self-healed somehow after the intake of fractures. There's some literatures and researchers have proved that. So that's actually one of the advantages of the clay rocks. But also there are limitations for clay rocks. We can say this rock is sensitive to almost everything, to temperature, to pressure, to moisture. So it's really hard to characterize. It's not like the granitic rock.
Yes. Thank you very much, Dr. Liu. I think you give a very wonderful talk, and your answering is very interesting also. But the time is up. I think Dr. Royota, could you please help me share the screen. I think we have to end this wonderful session in July. And yes, on behalf of the organizing committee, I would like to thank the ISRM for helping us in the organization of this event, especially Dr. Ignacio, and both Dr. Ryuta and I would like also thank Dr. Chun Zhu and Dr. Lang Liu for their very interesting and valuable presentations that addressed two relevant topics in rock mechanics and rock engineering. We hope that this seminar provides you new insights and new challenges for future research, and it could be a periodic event for sharing ideas about rock mechanics and related topics. For this reason, we want to invite you for the next seminar that will be virtually held in August. Dr. Wei Li and Dr. Hassa Toseni will present their works, especially on four-dimensional computed topography of granular force chains. And the other topic is coupled thermohydromechanic modeling of nuclear waste disposal in rock salt. I think both of the talk will be also very interesting. Further information about this event will be available on ISRM newsletter and website. So keep in touch not to lose the next webinar. And if you are interested in participating, perhaps contact us by the email. I think you can see the email from the screen. And thank you for your participation, and have a wonderful and safe day or night. And thank you, all the speakers, audience, and Dr. Ignacio and Dr. Ryuta. Thank you very much. Bye-bye.
Thank you, everyone. Bye.
Ignacio, I think we can close the conference, and you help me close the YouTube.
Yes, of course. You can close the conference.